Hello and welcome to today's seminar in the Smart Mobility Connection series. My name is Haji Shahab and I'm the Traffic 21 Women in Transportation Fellow. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the Mobility 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note this session is being recorded and all participants' microphones are muted. To ask a question, please send a message to the chat box. You do not need to wait until the end of the presentation to send your questions. Now, I'd like to introduce today's speaker. Mark McCord is a professor of civil engineering and city and regional planning at the Ohio State University, where he has been teaching and conducting research in transportation systems since 1983. His recent research focuses on innovative uses of automatically sensed data for transportation applications. Mark is co-founder and co-director of OSU's Campus Transit Lab, a unique living laboratory that changes advantages of OSU's large and diverse campus and sensor-equipped bus service to support transit and transportation-related research, education, and outreach. He is also the director of the Civil Engineering and City and Regional Planning dual MS degree in urban transportation planning. Mark received a PhD in Civil Engineering Transportation Systems from MIT and MS in Industrial Engineering from Stanford University and a BS in Civil Engineering from Purdue University, and has held visiting faculty appointments at the University of Paris, Dauphine, and University College Dublin. Please help me welcome Mark McCord as he tells us about his university transportation project, Central Project, co-authored with Rabi Mishalani, Benjamin Kaufman, Harsh Shah, and Sherzad Sharmche Tusi of the Ohio State University, monitoring roadway vehicle miles traveled using video imagery from transit buses and operational use. Mark, over to you.
There we go. I think I'm unmuted. And here we go. Oops, sorry. I'll start you my video. Okay. How's that? We set up, sorry for the delay. If you can't hear me, please let me know.
It looks great.
Okay, thanks. Okay, thanks, Haja, for the introduction. Hello, everyone. I'm pleased to be able to present some recent results we've obtained using imagery from OSU campus buses to estimate vehicle mile traveled by first estimating the traffic volumes on roadways. As I said, I'll focus on vehicle miles traveled in this presentation, but the methodology we've been developing in this project over the years has been to estimate traffic volumes from the imagery and then use those as an input to vehicle miles traveled in this application. Before I get into the details, let me just again recognize, thanks Haja for recognizing my co-investigators, colleagues on this presentation. Rabia Mishalani and Ben Koifman are faculty members at OSU, and they are co-PIs on this project. Shah Harsh is our present graduate student working on the project, and Shahrazad developed a lot of important aspects to this project before she graduated last summer. There we go. Okay. As I said, I'm going to focus on vehicle miles traveled, empirical vehicle miles traveled in this presentation, but the idea is we've used this methodology, we've developed this methodology to estimate volumes from bus-based video where the buses are in operational use. So I'll first give a quick introduction to vehicle miles traveled, which may be pretty obvious to many of this audience. And then I'll give what I'm calling here a review of, there we go. I'll give a review of what I call our methodology, the methodology we've developed. I'm calling it a review because we've presented aspects in this, the basic concept of the methodology in other Mobility 21 forums. Then I'll just briefly talk about some methodological improvements we've made to the approach and show that the empirical data show that these changes we've made actually do improve the methodology. Then I'll turn to using the methodology to come up with empirical VMT, vehicle mile traveled results, and interpret them to say, yep, we're getting meaningful patterns, and then turn quickly to say the alternative means of giving vehicle miles traveled. Well, I'll say right here that there are a lot of companies popping up these days saying we're going to come up and aggregate data from a variety of sources and provide that to practitioners. We're going to look at one of those. It's very popular in Ohio, remain nameless, but we'll see that our estimates are much, much better than what you would get from these popular location-based service companies. Then I'll just, again, quickly summarize and then talk about some ongoing efforts. So as I said, I'm going to focus on empirical vehicle miles traveled here, on estimating vehicle miles traveled from buses traveling around campus, but it can be any roadway. And so let me just give a quick overview of vehicle miles traveled. As I said, I think probably most of the audience here would be familiar with this. But VMT is the most common metric of network-wide travel. If I have a network of, in this case, the OSU campus or Columbus, Ohio, or the state of Ohio, and people say travel has increased in the vehicular travel has increased in the state of Ohio, they're usually talking about VMT. VMT is used for a variety of purposes, monitoring over time, just to see what's happening with the overall transportation travel and roadways, but for policy purposes, maybe for before and after studies. But let's just take it for granted that VMT is this metric that people are pretty much interested in. By definition, VMT is the sum of all the vehicles miles traveled on a roadway. So if I were to look on this network of roadways here, and I was going to look over a year, for example, I would say, look at every vehicle that traveled on this roadway. How many miles did it travel on any of the roadways in this network? And just sum those up over all the vehicles. And that's the vehicle miles traveled. That's hard to get. And so we usually calculate VMT as, we usually calculate VMT as going to a segment, figuring out the segment length, and then figuring out the traffic volume. How many vehicles use that segment over a year, for example, if I'm talking about annual VMT, multiplying the volume times the length and summing that up over all lengths, all segments in the network. That's the mathematical equivalent. I tell my students it's not the definition of VMT, but it's the mathematical equivalent. So we get every segment, we get the length of the segment and the traffic volume on the segment, multiply those together, add them up over all segments. Getting the length of the segment is pretty straightforward. We've got GIS, we've got ways to measure things immediately now, online lengths of segments. So that's straightforward. The tough part is getting the segment volumes on here over the time period you're interested in. And traditionally, we do this with traffic counts. There are different ways we try to estimate volumes, but traditionally it's traffic counts. And the traffic counts are usually done in a traditional way. We've come up through this project with a different way to estimate traffic volumes, if you want, converting observations on a segment to traditional volumes. And that's what I'm going to review quickly here. Again, I call it a review because we presented this in different Mobility 21 forums before, but let me just motivate it again. The traditional traffic counts, we try to go out and get a volume. A volume is the number of vehicles traveling on this segment over a specified period of time, a year. If we're talking about annual volumes, AADT, for example, we'll be talking about 8 to 10 hours in a day on this segment. So the volumes that go out there, and traditionally, I send someone out there and he just counts the number of vehicles passing over that time period. Or more likely, we go out and we put road tubes out there and we basically sense the number of vehicles passing over here, and we get the number of vehicles on the segment. But either way, whether we're doing manual counts or road tubes, I like to say we go out there and we stay there. And so we're staying there over time at one place, and we stay there for a long period of time. And these traditional traffic studies get obviously very good estimates of the volume. You know, there's always measurement error, but at very good estimates of the volume over long periods of time because the people are out there. But they only get them at the place where we put down the road tubes or the person's out there. And they only get them if we send people out there or if we put down road tubes and pay for the road tubes to go out there. And so the idea is we get it at limited locations of our network and on a very infrequent basis. We came up with the idea that buses travel all around an urban area. So they're covering the expansive roadway network, and they do it on a repeated basis. And at the same time, buses are increasingly being equipped with cameras for safety, liability, security purpose. I like to call it other purposes. The cameras aren't out there to do traffic counts. They're out there in case the bus is in an accident, who was at fault. If there's a problem on the bus, can we maybe see what's going on and get some security there? We said, since these cameras are out there, we noticed that they see the roadway out there and they're seeing vehicles out there. And so we said, can we take advantage of this existing imagery, the sensor, the cameras out there, you don't have to pay for it, the platform for the sensor, the bus is out there because it's transporting people back and forth. So we have the platform and the sensor, we have the data. Can we take advantage of this stuff that's out there for other purposes? We don't have to pay for it and come up with traffic counts. And that's the basic idea. Now, hopefully you can see when a bus traverses a segment, contrasting with the traditional approach where someone goes out there, a road tube goes out there for 3 days and counts traffic over 3 days. We're going to get one individual pass of a bus, maybe a minute to go over a traffic segment. It's going to be a very short observation. However, buses go over and over and over again, and different routes use the same segment, and we have multiple buses on the same route. And so we're going to get multiple samples of the traffic out here. And our approach is to sort of say, let's take these multiple samples, come in and see if we can get a good traffic volume. So, the way we work, the state of our practice of this approach right now is we get the video from the buses and we convert this imagery to digital information. At this point, we're doing it, I call it semi-automatically, but it's got a lot of human intervention here. We have a MATLAB GUI, a graphical unit interface. When a vehicle goes by, we press a button. Those frames that we record, we post-process those using the methodology we've come up with that transforms the volume, the observations of vehicles we get from what we call this moving observer into a traditional traffic volume. And again, we've presented this before, but let me give you a quick review. A traditional traffic volume would have an observer here. This is this eye at some spot and just counts the traffic coming past this location on the roadway over time. Our approach says, here comes the bus going this way. We're going to see the vehicles coming in the opposite direction. And so the observer would sit here and it would count the vehicles, and then it would say, how long was I out there counting the vehicles? And that would be the volume, the number of vehicles per that unit of time, upgraded to how much time we want the volume for. To sort of get this moving observation to convert to this traditional volume, the bus is going this way, so it's going to observe these vehicles at different times. All these vehicles the bus observes are going to pass the observer, traditional, no leakage on a segment, and then the bus is going to go on its way somewhere else. So how long would it take for this last vehicle to get down to the observer? We estimate that time. And it's not really the last vehicle. We want to know that there were no vehicles observed, let's say, after this last vehicle. So we imagine an imaginary vehicle up there. We call it a virtual vehicle. And we get the time that this vehicle would take to come down to the observer. And so all the vehicles the bus sees in this single pass over the roadway network, that's the number of vehicles. The time the bus takes to traverse this segment, that we can get from the GPS, that we call T1. And then the time for this virtual vehicle to come back to get down here, that would be the time when this virtual observer would wrap up her counting and go away. And so she would see N vehicles in the time the vehicle goes this way and the time that this last piece of observation would reach that person, T1 plus T2. And so that, usually we do T1 and T2 in minutes. So we multiply by 60, and that gives us the hourly volume. I know it's quick, but that's the basic approach. We presented it before. It's a modification of the moving observer method, which was out there years ago, decades ago, but it now accounts for just observing traffic in one direction, which is useful for what we're doing with the buses. As I said, think of it, the idea is I'm going to see N vehicles in the time T1 plus T2. May take the bus a minute to go up here and another minute to go up here. It's like a 2-minute count. This is going to be a very short observation to try to estimate, for example, an hourly volume. But again, the idea is we're going to have multiple bus passes within that hour, and we want to aggregate these bus passes. So for example, one bus goes past and uses our calculation to come up with V1 during the hour. Another bus goes past the same segment, either multiple buses on the same route or different routes using the same segment. It gets an observation that we convert to V2 for the hourly volume. The mth bus passes gets during the hour gets a hourly volume VM, and somehow we have to aggregate those. In our previous presentations, all we did was simply take the average of these guys and say that's an estimate of what we would have seen with a real observer out there for my hourly volume. That's what we've been doing before. We have a few, we have more what we call methodological changes, I'll call, to the video-based volume estimation that we've made since last time. Some we're working out, sometimes they work, sometimes they don't, but there's two I'm going to present here that definitely look like improvements. There we go. So here are steps. First, we convert the imagery to digital information. We've been in a side project, we've been working on automatic image identification. We're not there yet. We don't have anything to report. We're making some progress, but right now we're still using our GUI, our graphical user interface. But remember, the next step was on an individual bus pass, we estimate with this equation what the hourly volume was. And we noticed that there are some bus passes, because we're only going by for maybe a minute of observation, that we don't see any vehicles, n equals 0. So that would result in an hourly volume of 0. And we know that's a silly estimate because we know there's going to be traffic out there, even if it's one vehicle. So right now, we filter out those, we throw them away. We say, we're not going to use this individual bus pass. Next time the bus goes by, it may see some vehicles and we'll use that one, but we're not going to use bus passes with zero. Similarly, on the other end of the spectrum, we've noticed a lot of times a bus will go past and there'll be vehicles queued, either there's this bus stop stopping behind it or more regularly because of a traffic signal. And so we're going to see a lot of vehicles in a short time, and that's going to lead to an exceptionally high estimate of volume, more than you would expect on the capacity of the roadway, because after the bus passes the queue, it's going to see a lot less flow. So this queue is going to lead to a really high estimate of a volume that we think is too high. So we're eliminating those. We're filtering out bus pass volumes that are greater than what we think would be a surface road capacity. Right now, we're using 600 vehicle out per hour per lane. We're playing around with that, but that's the idea. Now, as I said, these are the two I'm going to talk about with empirical results. We're investigating other modifications like how to use the zero and not completely throw it out. It's information. How to use there was a queue, not throw it out. That's information. Haven't really nailed that one down yet, but the one is to filter these guys out, and you'll see that leads to improvements. The second thing, change we've made is we go out right now and we have to aggregate all of these different bus passes. So the dot here is going to be a bus pass at this time led to N vehicles in a T1 plus T2. That would be our estimate. And then we multiply by 60 to get an hourly volume. But we're going to forget the 60 for now and just call this a flow rate in terms of, let's say, vehicles per minute. So we're getting all these flow rates over time. And as I said, traditionally, if I were to look between 7:30 and 8:30, like an hour, I would take all the bus passes within here, get the individual flow rates, average them, and that would be our estimate of the hourly volume, multiplied by 60, of course. Now, that's not accounting for temporal variability within it, the hour, and there's some other aspects that I won't go into today to keep the focus on the VMT. But we said it makes more sense to think if this is a flow rate, the actual volume is going to be the integral of the flow rate over time. And so what we're doing when we're actually taking these flow rates and just getting an average over the hour, we're just sort of getting the integral, the area under the flow rate curve that looks something like this. We're going to explicitly take into account the temporal variability at a smaller time span by basically getting a flow rate curve. Right now, we're using linear interpolation. So each one of these is a flow rate. And so we're just going to connect it linearly, and then we're going to integrate over time. So now between 7:30 and 8:30, rather than take the average of these guys and say that's the volume, we're going to integrate under this curve and actually come up with the volume. And again, you'll see in a second that that leads to better estimates. So let's talk about the empirical results. So as part of what we do, both for research and you'll see for educational purposes and for outreach purposes, we collect data, and on some days we can get road tubes out there to simultaneously collect the actual volumes over there. And so what we're doing here is we're looking at a bus goes over, gets the volume in an hour, and at the same time there's a road tube out there and gets the volume in the hour. Let's take the difference of those two. That's sort of, we're going to assume the road tube is correct, but we know those of you who deal with road tubes know, we know there's measurement error in those two. But we use the road tube as a basis. We'll say that's sort of the error in our video-based estimation. And what we'll do is we'll take the difference in that and then take the absolute value just to get a magnitude of these differences. And so over 100 segment direction hours in 2018, the average magnitude of the error was 65 vehicles before we did this filtering of throwing out the the bus passes with zero volumes and those with overcapacity. After we do the filtering, it goes down to 56. In 2019, we had 80 segment direction hours of data. The average before we did the filtering was 116. After we threw out the bus passes was 0 volumes, or where we saw queues 100, etc. Similar, the same, what I showed here was when we use the old averaging method. When we use our integration method, where we sort of integrate under the flow rate curve, we still see that after filtering, it does better than before filtering. Similarly, if I want to look at how our integration method, looking under this curve rather than just taking the simple average of the volumes within the hour, we do better with the integration, whether we're talking about before filtering or after filtering. So for example, in 2019, if I filtered and just used the average method, on average, we'd have an error of 100 vehicles per hour. Now we're down to 28 vehicles per hour. So the point is, at this point, these are the methodological improvements that we think we do better with the integration method, with throwing out the 0 bus passes, throwing out the bus passes that have overcapacity. In the interest of time, I'll skip this next slide and try to move on to now the empirical VMT results. And here, we now, after these methodological changes, we're going to estimate the volumes on roadway networks using the integration method and the filtering to come up with VMT. We've been doing this for years. We only implemented these changes with the filtering and the integration method recently, but we had the old data, so we can go back and redo the data. In 2018, we monitored this network at OSU. This is the OSU campus. For those of you who know the football stadium, that's here. I'm sitting right up here at this moment. This is the OSU campus here. We monitored these roads. There were 6.3 direction miles of roads. We had road tubes on these blue segments. Those were 2.2 direction miles. We did it on one day at the end of October, or the beginning of November. In this case, it was the end of October on a Thursday. So traffic conditions were the same in 18, 19, 20, and 21. In 19, we added some more roadways. So we have more direction miles. MORPC, the people who provide the tubes, say they wanted to get counts on different segments. So they were on different segments. So we had 1.3 direction miles of road tubes, et cetera. We had a network in 2020 and a network in 2021. On this day, we get the video on other days, but we for monitoring purposes, we're looking at this Thursday, the end of October, the beginning of November. Classes are in session, so we expect homogeneous conditions on OSU. And we looked at, we collected video volumes from the OSU CABS buses, campus area bus service buses, while they were in operational service. In other words, they weren't doing this for us. They were out there in operational service. They had their cameras rolling in place, or were accidents or whatever. I'm not going to use this data at the time, but this is part of, we're not going to use this data for this presentation, but at the same time, we use this as a class project. We had students out there doing traditional traffic counts. As I said, MORPC, the Mid-Ohio Regional Planning Commissions, who's our metropolitan planning organization, they put down road tubes on a few segments. And so in this presentation, I'm going to compare the video data to the road tube segments when appropriate. Before looking at the comparison of the video data to the road tube segments, you'll see in about 5 slides that that's a pretty good estimate of VMT. Let me just say the 2018, 2019, 2020, again, we use the data, we process the data, we analyze, we interpret. A class, undergrads and grads, use this as a term project. We also use the outputs of our best VMT estimates. We do the VMT estimates. We don't use the student VMT estimates. And we provide this to OSU in an outreach function. So the idea of this project we've been working on for years is both research, education, and outreach project. Now, as I said, in 18, we did this network. In 19, we got a little bit better, so we could do a more expansive network. In 20, we did a little more expansive network. 21, about the same as 20. But what we're going to do now is monitor how VMT changed over time. So we're going to look at the vehicle miles traveled on this network here, which is a subset of these. So it's going to be the same network. And we're going to look at how the VMT over this network in 18 changed to 19 to 20 to 21. And here it is. This is the VMT from our video-based estimates after we did these changes of filtering and integration. In 2018, we had 18,673 miles, 19, this many miles, 20, obviously a big dip because this is when the pandemic was there. 2021, we got this. Starting to rebound, but not quite up to these levels. We take what we call growth factors, or what a lot of traffic monitoring people call growth factors. And we're going to get the growth factor with respect to 2018. So for example, in 2019, we had 19,000 vehicle miles over 18,000 in 2018. That's 1.02. So it looks like traffic increased by 2% from 18 to 19. That's in the range of noise. We think things are pretty stable there. This is exactly what we would expect to be roughly around 1. In 2020, when the pandemic hit and classes were closed, it dropped down to 56% of this value. So there's a drop of 44% of traffic in 2020 versus 2018. 2021, we're back to about 82% of the level we were in 2018. Traffic monitoring agencies, DOTs, come up with values of growth factors for their different classifications of roads. We looked at the ODOT growth factors for urban collectors, local roads, the type of roads you would expect on the type of roads that we're monitoring. And so ODOT's factor from 2018 to 2019 was 1.015, ours was 1.02. That's awfully darn close. Again, there's going to be differences. We're talking about one day, one area. ODOT's talking about all urban collectors that they can get the data for over a year, but that's pretty darn close. We notice, though, interesting, that in 2020, the ODOT factor is 0.916, ours is 0.6. And of course, this is over the whole year. Ours was on a day when the pandemic was there. If you can weight them differently, but the moral of the story is we on campus are seeing much larger impact of the pandemic than in regular travel. And it's not surprising, we're more flexible, we can do things at home, online, etc. But the idea is these are, under normal conditions, we're pretty close to what's being published, but we're getting local data. Under other conditions, as always, get local data because your local data in terms of what's going on in the campus may not be representative of what's going on in general urban collectors. We also looked at the growth factor as a function of hour of day. So just quickly, between 8 and 9 in 2020, the volume, the VMT across our network between 8 and 9 a.m. divided by the volume in 2018 was about 40%. In 2021, it was about 65%. Here's what happened with 2018 over 2018 is going to be a growth factor of 1, so that's going to be constant. 2019 is just all around this 1. That's why we're saying this is probably just day-to-day variability. But we're noticing this is kind of new, so we're not ready to say exactly, but it looks like the pandemic and the restrictions really affected morning commute and first evening commute also, maybe not so much in 2018, but the middle of the day was not affected as much. Again, in the interest of time, I won't try to interpret that too much. I would like to sort of turn to one last sort of empirical result here. And that's this as I said in the beginning, there are companies popping up around the country, I think around the world, who are aggregating data from a bunch of sources and selling them or selling subscriptions. Ohio is very much, I don't want to say enamored, but they work with one company to get a lot of their data. Through ODOT, who gives us a license, we can get that data. And we got the same data from this company to get their traffic volumes on the same days we did our traffic monitoring. And then we looked at our traffic monitoring on just the places where we had road tubes, and we got VMT over our day, now only on the segments where we had road tubes. And the road tubes, for example, in 2018, they came up with 7,600 vehicle miles traveled on the road tube segments. When we used our video data, we came up with 7,442. This company came up with 13,445 vehicle miles traveled. We were within 2% of what the road tube said. The company was with 76%. Here are the other numbers. Here are the VMTs themselves, but notice we're pretty close to what we were getting from the road tubes. And again, we're just using the video. We're not using the road tube data at all. We're just using the road tube to compare it and come up with these percent errors. Moral of the story is be careful using data from these suppliers. Yeah, we're not ready to supply this information on an operational basis like a big company, but the data looks pretty bad. Their data looks pretty bad. So in summary, the method we've presented before to sort of get this moving bus on a very short observation period, aggregate the things to come up with traffic volumes, we've come up with two changes we're presenting here, and they seem to improve performance. The last slide is our results using the transit bus video are really close to what you would get with traditional methods of road tubes. And they're a heck of a lot closer than what you would get, at least with this one company that's very popular in Ohio right now. We've also empirically, which we're also interested in, we've found how VMT, and we're monitoring it over time to see what are the changes, what are the effect of the pandemic restrictions on campus. This can be done anywhere on a research area. The research is generalizable. You could do this in any of your cities if you had the person power to convert the videos to the digital. But we're looking at as case study what happened on the OSU campus. We're still trying to do methodological improvements to the method. Again, I talked about we're trying to do better than just say the bus passes and I didn't observe vehicles, let's just throw them out. We're trying to do something with that information. I don't have time to discuss now. I could talk in the questions what we're trying to do. Our integration, we have the individual bus pass flow rates and we just connect with straight lines. We can fit fancier curves. We can smooth the flow rates. We've tried some of that. Sometimes it does better. Sometimes it doesn't. Whoops. We've been monitoring one day, same type of day every year to get an aspect of what's going on. But again, the benefit of these buses is they're going around time and time again, day after day. And so rather than really say what's happening on this one day, it would be useful to use this information to say what's happening on a typical weekday. And so we're trying to capture these multi-day observations. How much is there? And especially, can we capture them in the video? That's just started, but so far it looks pretty promising. We're also trying to come up when we have an estimate of the volume on a segment, what's the uncertainty associated with that, so you can sort of see how many passes you need to get a reduced uncertainty. We continue with our educational activities. Again, this project serves as a term project in a large class. We also obviously have lots of undergrads and graduate students working on the project as research assistants. And again, we use the outputs of our VMT estimates to give them to OSU planners. They don't get these VMT estimates in any other way at this point. These are the estimates we have. Here's the acknowledgements. I won't take the time to read them, but I'd like to especially thank, OSU, Transportation and Traffic Management, Beth Snoke, Tom Holman, Sean Roberts, who give us the videos when we need them. And it's not a trivial amount of work. If it ever got to be operational, things could be done to make it smoother, but very helpful in giving us the videos. I'll stop there. I'm not sure again where, and is it Joy or?
I am here.
Yep, good.
I have a few questions.
Okay.
How do you anticipate that the traffic patterns have changed in the past 5 years? Obviously, COVID has had a big impact on that. And then what do you predict will happen in the next 5 to 10 years?
How do in terms of predicting, we like to do forecasts. I do transportation planning. I haven't thought about it. I'm not predicting. And I haven't really thought of that. Well, let me you put me on the spot. I'll say this. The OSU campus is pretty big and pretty steady state. And if we didn't have this impact of COVID or not COVID, I would say it would be staying pretty steady. If you looked at the results we had here, I guess this is good enough. Here we saw that, there was a big dip. It's starting to come back. If you ask me, it's got nothing to do with this project. The project is give the data to those who are going to make the forecast. But I'm going to guess that it will continue to come back, but it's not going to reach this level we had here. And, when we first started this was before COVID. We were anticipating using this methodology, obviously across the world, if anyone wanted to use it. But at OSU, if they start coming up with policies, they're always talking about policies to reduce vehicular traffic on campus. And I won't talk about the policies now, but they have some to encourage not driving your car from one place to the other, but taking the bus or walking, etc. And we were going to use this to sort of document that those policies really reduce vehicular traffic. So in the absence of policies, I'm going to expect these vehicle miles to increase slightly, but not to here, not to what they were in 2018, just because we're all used to doing things differently now, but we'll see.
Okay. Are any of the segments 2-lane roads or traffic in the same direction as the bus cannot be captured by the video? How, if at all, do you account for directionality of vehicle volumes where volumes are higher in one direction of the road than the other in these instances?
Good. Yeah, that's very, very good. All of these roadways are two direction. And the benefit of this is the bus goes one way and captures one direction, another bus is going the other way to capture the other direction. So we just showed an example of capturing one direction, but we've got buses going in the other direction. Buses are in an urban area. Oops, there. In an urban area, most of these places are going to be two-way streets with buses coming in both directions. So when they only go one direction, we'll only get one direction, but traffic monitors have directional splits they could use. So getting information in one direction will be helpful, but most roadways will be two direction and buses are going in different directions.
Okay. Would your system work in extreme situations? For example, during a football game?
During a football game, I don't think people are going to be too interested in what's the traffic volume on the roadway. They'll be interested in where the queues are, how long are the queues there, and there'll be two issues. I would say this isn't targeted for those conditions. One, because getting the queues is different than just estimating the volumes. Two, during the football games, the vehicles are not traveling over the whole network. They have very specific route. The bus routes would not be traveling over this whole network like they do here. They come down this way and travel this way. So no, this would not be designed for that. One, because the buses aren't traveling in the regular operations during football games. And two, because the queues would be a bigger problem at that time.
Okay. What are you finding is the biggest challenge in this field at the moment? Are you finding that COVID is making it harder to get information and is throwing things off? Or what do you think the biggest challenge would be?
COVID's not, COVID's no problem, because as long as the buses are out there, we can get the information. So COVID's not affecting. That's the beauty of this. The buses are out there getting the data for different reasons. If you were to say, what's the biggest challenge to making this operational? I would say the biggest challenge to making it operational is, I'm not finding it here, is being able to translate this imagery effectively to get the cars. Right now, we get the video and we put this in a MATLAB and we can run it at 2 or 3 times speed, but we have relatively inexpensive undergraduates sitting there pressing the buttons, counting the cars. That's still very labor intensive. The biggest challenge would be getting an automatic vehicle identification that says, this goes by, there was a vehicle here. That, to me, is the biggest challenge to make it operational.
Okay. What is your favorite part about doing this research?
Well, that's a good question. I couldn't tell you favorite. Here's parts I like. One, I love, in the introduction, thank you for introducing me that way. I like to say there's stuff out there, in this case, video, that's out there for other purposes. Can we be clever and use existing data that we don't have to pay for to come up with novel applications? And so I like doing that. And it's really cool when the results look so good. So I really enjoy that. I love the fact that we do this on our campus, so we get to work with the transportation and traffic management group who runs the buses on campus, and they say, hey, this is cool, we'll help you out. So I like those interactions. And finally, this sort of contradicts what I said before, if we get this video processing, we won't need the students to press the buttons, but I like working with undergraduates. I like getting really good undergraduates in my lab to sort of press the buttons for us, and I like working with them. So it's multidimensional. I can't pick a favorite. I like the question.
Okay, and as a student interested in a career in research, what is something that you've learned during your career that you think a student should know?
Well, okay, I haven't seen who's on here, so I don't know how many people know my cynicism. I'll keep out the cynicism, like publications have to be, for one reviewer said this result, yeah, it looks good, but it's too simple. We need a fancier methodology. So I'll keep the cynicism out of that. But for my career in research, I didn't start out trying to do traffic violence from video. That applications change, and so there's some basis to research that you learn, but you got to be flexible to the applications. And again, my cynicism is, I see in the university, we often hire people that do one thing because they can do this one thing really well and make a career out of it and tweak the edges. But applications are going to change. And I never foresaw this. I never foresaw probably the 5 or 6 different big applications I've done in my career. They weren't something I envisioned. So be open to new applications, get the methodological skills and sort of the data analysis skills, those things are transferred.
Seems like that's good information for life as well as careers and research.
Yeah, well, yeah.
That is actually all of my questions today. So thank you very much, Mark.
All right, thanks. Thank you, Joy. Thanks, everyone who was here. I appreciate your attention. I really like the questions. Thank you. I hope I can get those questions afterwards, Joy. Bye,
Absolutely.
All
everyone.
right. Well, thank you, Mark, for sharing your work. And to all of today's attendees, thank you for joining us. As was mentioned earlier, today's presentation is going to be posted on the Mobility 21 What's Happening page of the website, as well as a video link to the session if you want to rewatch. This afternoon, you'll be receiving an email asking you to take a short survey about today's SMC. So please take a couple minutes to provide your feedback. And then finally, I want to plug students who are interested in engaging in transportation topics at CMU. We have the Transportation Club here on campus, and that's a great way to plug into transportation topics with fellow transportation nerds. So thanks very much for attending our Smart Mobility Connection seminar today. And please watch your emails for our next series, which will feature Helen Loeb. So thank you very much, everybody, and feel free to reach out with any questions. But if not, have a good day.